we want to discuss first is things that you may know very well and have worked with a lot up to now, but maybe you haven't thought of them in ways that mathematicians think of them, in a more abstract way. And let's start our discussion. So the first set of numbers that I want to discuss is denoted with a capital N, but with a double leg here. And this is what we call the natural numbers. So what are the natural numbers? The natural numbers are the set. So these squiggly parentheses denote a set in mathematics, just a collection of things. That's called a set. And it's the set of all the numbers with which we count apples or bananas. So it's 1, 2, 3, 4, etc. There are quite a lot of them, okay? And you know these. You know these ever since you were probably 2 or 3 or 4 years old. And in fact, you even know how to add these and subtract these and maybe multiply these. So these are called the natural numbers. And the letter N we use to indicate them comes from the word natural. The next set that we want to discuss is the set with which we denote by a Z with a double leg here. And this is the set, remember, this indicates a set where we take all the natural numbers, 1, 2, 3, etc., but we also throw in a very important number called 0, and we throw in negative integers, -1, -2, -3, etc. So there are dots going in both directions here. And these are called, the name of these numbers is the integers in English. And Z stands for Z in integers. Right, there is no Z in integers, and the Z in fact stands for the German word for numbers, which is Zahlen. So Z stands for Zahlen. Z in German is pronounced Z. So it's Zahlen. I think this is how you spell it in German. And that's where the letter Z originates. These integers came to the world, or at least the negative ones, when people realized, and you may have even gone through this experience on your own when you were in preschool, that if you try to subtract, let's say 2 minus 4, there is no answer in natural numbers, but it makes perfect sense to ask, what is 2 minus 4? I have $2, I paid somebody 4, now I'm in debt, how much is my debt? What is 2 minus 4? Okay, so these are the integers, and before I point out some facts about them, I want to throw in a bit more notation. We're learning a language here. Math is a language, and notation is part of it. Writing it is part of it, and it takes time to get used to, so please stop me whenever a symbol or a term or an expression is not clear. Always stop and ask. So, for example, 0 belongs to the integers. So this little symbol, which looks like a lowercase c with another line in the middle, means belongs to. That's the meaning of this little symbol. So 0 belongs to the set, so remember that this denotes a set, belongs to the integers. Some more notation. 0 does not belong to the natural numbers. Do you agree? This is a bit controversial, by the way, because in various places, the natural numbers are taken to include 0. It's a matter of convention, and there's no agreed on convention. So some people consider 0 as a natural numbers, and I will stick to the convention that it's not, that it's an integer but not a natural number. And some more notation, the set of natural numbers is contained, bigger c but a longer c, in the integers. Okay, So this means contained or included in. So here we have an element that belongs to a set, and here we have a set that is contained in another set. Okay, do you see the difference between these two notions? Okay, so this is just a bit of notation which we will gather up and pick up as we go along and gradually get used to. It takes time, but once you get used to it, it's just part of your it's so natural that you don't even give it a second thought. Okay, now if you think of Z here, of the integers, it's not just a set. Okay, it's not just a set. There are operations on Z. We know how to add numbers, we know how to subtract numbers, how to multiply numbers, how to divide numbers, and these operations come along not just with the actual operation, but with properties of the operation. So we know, for example, that 1 plus 3 is the same as 3 plus 1, right? That's called commutativity of addition, okay? So if we look at Z and we try to think, what are its properties? Forget what it is. Forget what it is. Try to collect only its properties. That's the idea of making something concrete, taking a concrete example and making it abstract, revealing the underlying abstract structure that may be common to Z and maybe to lots of other things. Okay? And if we understand the abstract structure, we can understand at once many, many things that have the same abstract structure. And that's what I want to do. I want to start it very lightly by revealing just part of the structure of Z and calling it a group. So let's write what we said. So Z is not just a set. It's not just a collection of elements, okay? It has operations. There are operations involving the elements, like addition, subtraction, multiplication, division, right? There are a lot. Let's indicate this by a little X, okay? And from this, we want to extract the abstract structure of Z. And, and I want to say there are operations that satisfy properties. Certain properties, like, for example, 2 plus 5 plus 3 equals 2 plus 5 plus 3. And it doesn't matter if I first add 2 and 5 and then add 3, or I first add 5 and 3 and then add 2, right? This property has a name. It's called associativity, right? And another property is that there is this 0 element, which when we add it to any number, it doesn't change anything, right? So 0 plus whatever is whatever. Okay, so 0 has this unique property of being what we call an identity. Okay, it doesn't see, or the operation of addition doesn't see 0. Okay, and another example is, for example, if we take 7 and add minus 7, we get 0. So there are these things that we call inverses. Addition has inverses. Every number has a minus number, which when we add them, we get 0. Okay? So trying to collect these, we get what we call a group. Z with the addition operation is a group. What is a group? What is a group? So take a deep breath, and now I'm going to write something completely abstract. Completely abstract. something that's living in the mind of a mathematician, or in your mind soon, okay, which after I write, we're going to see that Z is an example of that notion of a group. Okay, so what is a group? Here's the definition. The definition. A group, that's what I'm defining, is a set. A set is just a collection of elements together with an operation on the elements of the sets. Operation on the elements of the set, which we're going to denote by a dot, but it's kind of a bigger dot, a tiny little circle, a tiny little O. That's how we're going to denote the operation, as not to confuse it with any existing operation that you know on numbers. Okay, so it's abstract, which satisfies the following axioms. So if you have a set, a collection of things, together with some operation defined on those things that satisfies the properties that I'm going to write down now, which are sometimes called axioms, then that set is a group. So here are the properties. The first property is called closure. Closure. And what it means is that for any, so let's introduce a new symbol here. For any, so this upside down capital A is the symbol which indicates for any, for each, for every, doesn't matter. So for any two elements, A and B, oh, I forgot to call it, to give it a name. So a group, let's write it here, a group G, let's call it capital G for group, is a set together with an operation which satisfies for any two elements A, B, which belong to G. Which belong to G. This is a symbol we already met. It holds that A and B, when we operate on them, the result also belongs to G. Okay? So as I'm writing these things, and you should feel a bit shaky, whoa, this is too abstract for me, think example. And our example that we're looking at simultaneously is the integers with addition. So if G is the integers, and this operation here is addition, if you take any two integers and add them, the result is going to be an integer. This, for example, is not true for natural numbers. Oh, yes, it is. Right. Okay. That's not what fails. You're right. You're right. Sorry. So for any two elements, if we add them, the result is also an element of the group. Okay. For natural numbers, we're going to see are not a group, but not closure is what fails. Something else. We'll see in a minute. Okay. The second property is associativity. Which means that for any three elements, if you operate on the first two and then throw in the third one, it's the same as if you do it. All these are little dots. If sometimes they seem full, it's because the marker has a kind of a bold font. Okay, so this is associativity, and this is true. Let's stick to the formalism. For any A, B, and C which belong to the group. For any three elements, doing the operation, composing according to the operation, is independent of the order in which you work. Okay, that's the associativity property. Property number 3. Here's some more. This is the identity. This is what it's called, identity. So by the way, property number 2, we know for addition of integers, right? That's what we mentioned earlier. So the identity says that there exists, so this symbol here, which is E facing the wrong way, so this means exists, there exists, and you can remember it by for any is an upside down A and exists is a backwards E. Okay, there exists an element which we usually call little e in the group, which serves as an identity, meaning that the operation doesn't sense it. Okay, so what does it mean? Such that ST is a brief way of indicating such that, yeah, I'll write it, sure, such that. Okay, it takes time to get used to all these abbreviations and symbols, but that's part of establishing a language. Okay, so such that if we do A operating on E, and likewise if we do E and operate on A, independent from which side, what we get is just A. Think addition, and what is the identity for addition in the integers? Right, it's 0. So when you do 3 plus 0 or 0 plus 3, you just get 3. Okay, the operation doesn't sense the identity. And here we should add for every A that belongs to G. Okay, can you feel that you gradually can start reading through this? Okay, if you would enter the class now, being just, 20 minutes late to class, you'd feel, whoa, what's going on here? Because you have to see it gradually and pick it up slowly. The fourth property, which is the property of the inverse, says that for every element in G, for every A that belongs to G, there exists an inverse element. For any A in G, there exists an inverse element which we denote by A to the minus 1 usually. A to the minus 1. Sometimes we denote it by minus A. Let's stick to this notation. Usually it depends. Let's write, I'm debating here. Let's call it B. There exists a B in G. Okay, so for every element, there is another element such that if we compose the two, A composed with B, we get the identity element. Okay, so for the integers with plus as the operation, if you take 7, what is the element that you need to take such that when you add it to 7 you get 0? Right, minus 7. And that's true for any number. If you take minus 5, the number you need to add is minus 5, which is 5, right? And then you get 0. Okay, so an example of a group, Z with plus is a group. Let's add here, Z with plus is a group. Let's add here, E, the identity is 0. That's the identity for the integers with addition. And minus A is the inverse of A. Right? That's the inverse for addition in the integers. Is everybody following? Okay, this is, we just took a great leap in mathematical thinking, which you may have not done ever before. Okay, but this is very important in mathematics and in all of the fields of mathematics. And it just takes time to absorb. Okay, so is everybody with me? Did everybody follow what just happened here? Okay, and you may need to pause and to think a bit. Think about it a bit. Try to express all these properties for Z with addition. Okay, just like we did in the examples that preceded this notion of a group. Okay, and by the way, the natural numbers where we don't have 0 and the negative integers are not a group because there's no identity. 0 is not a natural number. But even if you decide to include 0 in the natural numbers, there are no inverses, right? -3 is not a natural number, and therefore the operation doesn't have inverses. Plus doesn't have inverses, okay? So Z is called an additive group, a group where the operation is addition. So let's add a few more remarks. So one more example. N, as we mentioned, with plus, sometimes we denote it like this, the set and the operation is not a group. No inverse and no identity. Two properties are not satisfied. Okay, clear? Good? Okay. Yes, question. Very good, very good. So the question is, why did let's go back to this board for a second. Why did I pick up only these properties? There are more properties, right? For example, we mentioned commutativity. Okay, for example, we mentioned the property that A plus B is the same as B plus A. Why didn't I write it here? And you can ask even furthermore, why did I completely ignore subtraction, multiplication, division? There are many other, there's much more structure to Z than what I expressed here. And that's true, okay? So in this case, I'm defining an abstract thing that Z is an example of, but Z is something more, in fact. And we're not going to discuss it here. This is only in kind of a first course in algebra. But Z is in fact something called a ring, which has more properties, okay, and more structure. Okay, so this is kind of only extracting some part of the properties, which are satisfied for many, many things, including things that are not necessarily have other properties. Okay, so let's write some of that down. So remark, very good observation. Remark, a group that satisfies another property, namely that A operated by B equals B operated by A, okay, so A plus B equals B plus A for addition, is called, for any A and B, is called N. So this is the property of being commutative. It's called either an abelian group, named after a mathematician that we mentioned in the introduction, Abel, or sometimes it's called a commutative group. Okay, and so an example would be Z. Z with addition is a commutative group, is an abelian group. Okay? And you may ask, aren't all the operations in the world abelian, and the answer commutative? And the answer is no. So even in this course, we'll see, for example, matrix multiplication is not commutative. If you take two matrices, and if you don't know what a matrix is, you will soon. If you take two matrices and you multiply them, A times B is not the same as B times A. So not every operation is necessarily commutative. Okay? And yeah, in fact, if you take subtraction is not, so here's another remark. I don't want to go too deep into these issues, but it's interesting and it's good to mention. Matrix multiplication is not commutative. And subtraction in Z, in the integers, is not commutative. So matrix multiplication you don't know yet. We'll see that later on. But this you do know. So for example, if you take 1 minus 3 minus 2, that's not the same as 1 minus 3 minus 2 if you do it in two various ways. So if you do 1 minus 3, 1 minus 3 is negative 2, minus 2, that's negative 4. But if you do 1 minus 3 minus 2, that's 0. Okay, so, oh, this is not associative. Sorry. I'm sorry. You're right. So matrix multiplication is not commutative. Subtraction in Z is not even associative. So there we go. We have things that are not associative and we have things that are not commutative. So this we will see later. Later is in a few weeks, but later. Okay, so not every operation is necessarily commutative, not every operation is necessarily associative. Okay, does everybody agree to this? Okay, and good. Okay, let me ask you one more thing. I'm tempted to ask you at least one more thing. So here's my question. Suppose we take the integers. Suppose we take the integers. So let's call it an example. Suppose we take the integers with the operation of multiplication. Is it a group? Is it a group? So what you should be doing now is looking at the axioms of being a group. There they are. It's a set. Yep, it's a set. It has operation. An operation. Yep, the operation here is, look at this board, please. Thank you. It has an operation. The operation we're looking at now is not addition, but multiplication. And we're asking, is it closed? Is it associative? Is there an identity? What's the identity for multiplication? Right, it's 1, right? Anything times 1 is the anything again. 7 times 1 is 7. Negative 3 times 1 is negative 3. And are there inverses? Right, that's what fails. So if you take 7, can you find a number which when you multiply by 7, you get 1? You get the identity? And the answer is no. There is such a number. It's called 1 over 7, or 1/7, but it's not an integer, right? You have to expand your world beyond the integers, and that's what we're going to do next. So, example, Z with multiplication is not a group. There is an identity. There is an identity, 1, but no inverses. Since 1 over A If a is an integer, 1 over a is not an integer anymore, and we know how to denote it formally, does not belong to z. Clear? That's what fails in the integers with multiplication being possibly a group. Okay? Okay. So our next step is to expand. These numbers do exist. We all know 1/2 and 1/3 and 3/4 and minus 7 over 17. These numbers exist, and we want to add them to have multiplicative inverses. And that is another set of numbers called the rational numbers, stemming from the word ratio. So let's go back to this board. Let's go back to this board and write down the rational numbers. Add them here to this list. So the next set of numbers, denoted by q, with a double leg. Well, q doesn't really have legs, so we just double this circle-ish part of q. And q is the set of numbers of the form m over n. The set of numbers of the form m over n such that, so this vertical line means such that m and n belong to the integers. And one more thing we have to say whenever we write something like this. Very good. N cannot be 0. So these are called the rational numbers. That's the name of this set. And the q here comes from the word quotient. Because the rational numbers are in fact quotients of integers. Okay? So can you read through this? The set of elements of the form m divided by n such that, or satisfying that, m and n, the numerator and the denominator, are both integers, but n cannot be 0. Dividing by 0 is not defined. Okay? So these are the rational numbers. Using some notation that we had before, for example, we could write, let's pick up a bit more notation. The integers are included in, but not equal to, the rationals. So let's figure out why this is true. Because, wait, we said -2 is an integer. Do you see -2 in the rationals? Right. -2 is, for example, -2 divided by 1. We do some identification there. We say that -2 divided by 1 is nothing but -2. So in that sense, the integers are included in the rationals, included but not equal to, because there are rationals which are not integers. For example, 1/2. Right? Everybody good? Okay. And if you think for a minute, in the naturals, we couldn't solve equations of the form 3 minus 4 equals. It wasn't defined. But it was defined in the integers. In the integers, we can't define equations, we can't solve things of the form 3 times x equals 1, right? Because x has to be 1/3. But we can solve those in the quotients. Okay, so this added the inverses for addition, and moving on to q added the inverses for multiplication in the integers. Okay, everybody with me? Okay, so let's write that. Let's write that in more sophisticated, fancy words that we now know. that we now know. So Q, and these are things you have to think about. You have to think about. Q with plus is a group. It's even abelian, is a commutative group. You have to think about this. You have to look at the definition of what being a group is and think, is it true that 1/3 plus 5/17 is the same as 5/17 plus 1/3? That's what being commutative means. Okay? Is there an identity element for addition? Yes, it's going to be 0 again. Is it true? Does every number have an inverse? What's the inverse of 5/17? Negative 5/17, right? So it's rather easy to believe that. Q with plus is a group. Now, what we did is we threw in the inverses for the multiplication, right? Those are all these fractions here. So is Q with multiplication a group? And the answer is almost. Something still goes wrong there. And what goes wrong is that there is one single element which doesn't have an inverse. Okay? So remember that for multiplication, the identity is 1, right? Something times 1 equals the something. Okay? And the inverse should be a number that when we multiply by it, we get 1. And if you take 7 and want to get 1, you multiply by 1/7. If you take 3/4 and you want to get 1, you multiply by 4/3, right? Right. What about 0? Okay, so 0 does not have a multiplicative inverse. Okay, there's nothing you can multiply 0 by and get 1. Okay, so this is not a group, but if we remove 0, so Q without 0 with multiplication is also a group. Okay? So Q has, in fact, two structures here. It has an additive structure, by which it is a group, and it has a multiplicative structure, by which it's almost a group, but if you throw away the additive identity, it is a group. Okay? And these two structures combined is also, by the way, a commutative group, right? Multiplying is also invariant. It doesn't matter in which direction you multiply, right? And in addition to Q being a group and almost a group with respect to two different operations, there's a connection between these two operations, and that connection is called distributivity. Moreover, plus and times are related by what we call distributivity, the distributive law, distributivity. Wow, this is a crazy word. Distributivity, namely that if you take, let's just do an example. If you take 4 and multiply it by 3 plus 5, that equals 4 times 3 plus 4 times 5. Do you agree? This is called the distributive law. Okay? And a set that satisfies all this, namely that it has these two operations with respect to both which it is a group, and these operations are related by the distributive law, is called the field. Q is a field. Okay? And What I want to do, but that's going to be in the next clip, in the next lecture, I want to write down the axioms of being a field. For being a group, there were 4 axioms only, plus a 5th axiom for being a commutative group. For being a field, there are going to be 11 axioms. 5, which namely say that it's a commutative group with respect to one operation. Another 5 that say that it's a commutative group with respect to the other operation, excluding the identity for the first operation. And the 11th axiom is going to be this distributive one. Okay, that's going to be the definition of a field. And I'm going to do that in the next clip. And in the next clip, I'm also going to mention that there are more fields. So are the real numbers, and we'll mention what those are next. The real numbers, which are denoted by an R with a double leg, and the complex numbers. And complex numbers, maybe some of you haven't even seen before, but we are going to study them from scratch. We're going to introduce them and learn them from scratch, so you don't have to worry. They're denoted by this C with a double leg, C for complex and R for real. Okay, so these 2 other sets of numbers are also fields. So what I want to do next is to say what a field is and see that in fact these sets are indeed fields. So that's coming up next.